Hello everyone, my name is Lindsay Oftelie. I am currently a Marie Curie Fellow at the CNR in Pisa, Italy, and happy to join you today here in Grenoble. So today I'm going to tell you kind of an interesting story about dynamic cooling of qubits on quantum computers. So I'll start with some motivation on why we're interested in cooling qubits in the first place. And it comes from kind of two fundamental areas. The first is what's known as DiVincenzo's criteria, which are 5 criteria that are essential for a physical system to operate as a quantum computer. And one of these, highlighted in red, is the ability to initialize qubits into a simple fiducial state. So generally on quantum computers, we assume that our qubits start in the pure zero state, 100% in the zero state. And this actually corresponds to a qubit being at 0 temperature. And so you can kind of think of pure qubits and very cold qubits as interchangeable things. So we need to cool qubits in order to get them pure enough to act as our simple fiducial state for the initialization of a computation on the quantum computer. So that's fundamental, absolutely. Looking forward for quantum error correction, which will be necessary moving into the future, most quantum error correcting schemes require the addition of pure ancillary qubits throughout the computation. And so here also we'll need very pure or very cold qubits. So we need cold qubits now and in the future for quantum computers. Okay. So how can we cool qubits? Well, there have been a number of techniques developed by experimentalists over the years for cooling qubits via physical methods like lasers or magnetic fields. But these are very expensive, energy intensive, money intensive. So scientists begin to think about, can we cool qubits in other ways, perhaps algorithmically with circuits? And so this led to the introduction of dynamic cooling. I think there's a very low battery on this. Which was put forward in, there's another one, that's okay, which was put forward in 1999. And the idea of dynamic cooling is you have a group of n qubits, you have one target qubit that you're trying to cool, you apply a global unitary to all n qubits, and you cool your target qubit at the expense of heating up the other qubits. Now, this is a closed system, right? Our unitary just acts on our n qubits. And so because of this, the amount you can cool your target qubit is limited by what's called Shannon's bound. And this is because the entropy of a closed system cannot decrease. And so at the time that this was put forward, the quantum computers in vogue were the NMR quantum computers, nuclear magnetic resonance quantum computers. And these quantum computers had qubits at very high initial temperatures. And in this high initial temperature regime, if you look at this Shannon bound, the limit it sets is that the amount your target qubit can be cooled is going to be limited to 1 over the square root of n, where n is the number of qubits you're using. Now this is very poor scaling, and they were looking at it, and it seemed like if you wanted to cool one target qubit, you would need on the order of tens of thousands or even millions of qubits to get to sufficient cooling power. And so this was unacceptable for the quantum computers at the time. So they started to think about, how can we beat Shannon's bound for these high initial temperature quantum computers? And the way you can do that is by opening up the system. So this led to a whole flurry of results in what's been known as heat bath algorithmic cooling. Here we open up our system. And this is how it's done. You commence in 2 phases. In the first phase, you do a round of dynamic cooling, which basically shifts energy from your target qubit to the auxiliary qubits. And then in a second rethermalizing step, you allow a subset of reset qubits to interact with the environment to rethermalize back to the bath temperature. And then you can again do a round of dynamic cooling to pump energy from your target qubit to the auxiliary qubits, which will rethermalize with your bath. And you're kind of pumping entropy out of your system in this way. And with this, you can beat Shannon's bound and cool to even lower temperatures. So this looked extremely promising. The one kind of subtlety here is you actually need two species of qubits. And this is because you have your computational qubit, like your target qubit that you're cooling. You want this one to have a very long decoherence time. It needs to hold its information for as long as possible for you to do computation with it. But your reset qubits, you want to have very short decoherence times, really short relaxation times, so that they can rethermalize with the bath quickly, so that you can do multiple rounds of cooling. And this was okay for NMR quantum computers, which have nuclear spins, which can serve as the computational qubits with long relaxation times, and electronic spins that can serve as your reset qubits with short relaxation times. So a ton of work was done on this. Many different flavors of heat bath algorithmic cooling were developed. This looked great, and essentially there was a dominance of heat bath algorithmic cooling for these NMR quantum computers because they had this high initial temperature, so they needed this open system cooling, and they had the availability of two species of qubits. So a long road over 20 years of heat bath algorithmic cooling was commenced on. Dynamic cooling was almost entirely abandoned, and everything was kind of left off around the early 2000s. Fast forward 20 years, and we now have our contemporary quantum computers. NMR quantum computers have almost wholly fell off by the wayside. We have our superconducting circuit quantum computers, our neutral atom quantum computers, our trapped ion quantum computers from a range of different companies and academic institutions. And unlike NMR quantum computers, contemporary quantum computers have two attributes. They have identical qubits. We don't have these two species of qubits anymore. This is going to make heat bath algorithmic cooling very difficult to implement when we only have qubits with long relaxation times. However, all of our contemporary quantum computers are now initialized at ultra-low temperatures. We have very low initial temperatures for our qubits. So we thought, is it time to revisit dynamic cooling on contemporary quantum computers? So we delved in, and let's take a look at our system again. So we have our system of n qubits that we're going to act our global unitary on, and I'm going to define two parameters. We have this P1, which is the probability of our target qubit being in the 1 state before we commence any of our dynamic cooling, and this probability is set by the initial temperature of our system. And we have P1 prime, which is the probability of our target qubit being in the 1 state after cooling. Now this should be lower, right? We want our qubit to get to almost 100% in the 0 state. So we're trying to minimize this P1 prime. And I'll note that we can actually, because we're working with two-level systems, we can equate this probability with a kind of pseudo-final temperature. Now, it's not a temperature in the sense that it's, the system's in equilibrium with some bath at this final temperature in the way that this initial temperature is, but we'll equate this final probability with a final temperature so we can kind of see the cooling that's occurring in this qubit. Okay, so maximal cooling. We want to see how much cooling dynamic cooling can do for our system. And so essentially that's looking at minimizing this P1 prime. So we looked at our problem, we looked at the optimal cooling that dynamic cooling can do, and we were able to find this equation for the final probability of the target qubit being in the 1 state as a function of the initial probability and the number of qubits n. Using combinatorics, you can derive this. And again, as I said, we can kind of write these probabilities in terms of temperatures. And so it's very helpful to rewrite this equation in terms of the final temperature, the final optimal minimal temperature you can reach with dynamic cooling in terms of the initial temperature and the number of qubits n. And if you plot this, you learn something very interesting. So what I'm plotting here is the initial temperature on the x-axis and the final temperature on the y-axis. The black dashed line is just when they're equal to each other, so anything below this means we're cooling our target qubit. The different colored lines are different system sizes. S is just n over 2, so you can just think of it as the number of qubits. So we're increasing our system size as we go down. Now, if you look in the high initial temperature regime, you see that these lines are very close together. As you add more qubits, you don't get a lot of bang for your buck. And indeed, if you go to the high temperature limit, we find that the final temperature scales as this 1 over square root of n, which was initially found in these back-of-the-envelope calculations. So we've confirmed this was the case. However, in the low initial temperature regime, these lines start to spread out. And so you're getting more cooling the more qubits you're adding. And indeed, if you look at the low temperature regime, our final temperature now scales with 1 over n. So much improved scaling of dynamic cooling on our low initial temperature qubits, on our contemporary quantum computers. So this is good news. It looks like dynamic cooling will work a lot better on our current quantum computers. This line kind of indicates kind of the area where our current quantum computers are operating. And so you see they are entering this regime of this low temperature where dynamic cooling is much more effective. I'll also quickly note, since this is a conference about energy, that we looked at the minimum work per qubit required for dynamic cooling as a function of the initial temperature of the qubits. And you see in this low temperature regime, it's exponentially decreasing, which is good. Here's a kind of this inset is a zoom in of where some contemporary quantum computers, where their initial temperature puts them on this plot. And so you can see dynamic cooling is a lot more effective on our current quantum computers, and it's a lot more efficient, right? The amount of work we need per qubit is exponentially vanishing as we go to lower and lower temperatures. Wonderful. So effective, efficient. Will dynamic cooling work on contemporary quantum computers? This is, of course, the major question. And it doesn't look great because the circuit sizes, right, when you convert this global unitary into a quantum circuit to enact it on your qubits, it appears to grow exponentially with system size n. And this is not good because we know that our current quantum computers are quite noisy. Longer the circuit, the more errors, the more likely it will not work at all. So we wanted to look at how dynamic cooling actually performs on noisy quantum computers. And we start off by doing some simulations on an emulated noisy quantum computer. So this is an application on a classical computer that emulates the performance of a noisy quantum computer. And we looked at two initial temperatures. That's what these two different plots are. Across the x-axis is an effective error rate. We used a noise model that is parameterized by just one parameter to keep it simple, so we can kind of look at how noise scales with error, or how this cooling scales with error. So we have our error rate going on the x-axis, and we have the final temperature on the y-axis. Recall we start at this temperature. And the different colored lines are the different system sizes. Now, you can see that at low error rates, we have systems with 3 and 4 cool the same amount, 5 and 6 cool the same amount, 7 and 8 cool the same amount. This was expected. If you add one more qubit to an odd number, you don't get any more cooling power. However, as you increase the amount of noise, you see these lines split. And that's because the circuit for a 4-qubit system is going to be larger than the circuit for a 3-qubit system. So even though it has the potential to cool the same amount, when the circuit's larger, the error will be larger, and you'll get less cooling. One interesting thing to note is when we start at a higher initial temperature, the point at which noise starts to have an effect is later. And so what this is saying is essentially the lower temperature the qubits are starting at, the more of an effect noise is going to have. Okay, so this doesn't look great, right? Like as soon as there's kind of moderate levels of noise, these lines shoot up over the initial temperature. So we're actually heating up our system instead of cooling it. So how can we actually make dynamic cooling work on quantum computers? We looked at a suboptimal cooling method. And this is where you give up a little bit of optimal cooling power, and in return, we're going to get massive reduction in circuit complexity. So here's how our scheme works. We now have n qubits, where n is equal to little n raised to the r. So take, for example, 9 qubits. We're going to divide these into clusters of size little n. we're going to perform dynamic cooling within each of these clusters. We're then going to divide the cooled qubits into clusters of size n, and we'll perform dynamic cooling within these cooled qubit clusters. And so in this way, you can do, if you are using cluster sizes of little n, you can do r steps of this suboptimal dynamic cooling. And so what you get, in this example at least, little n was 3, r was 2. Your circuit is drastically simplified. You basically have some number of dynamic cooling on the small clusters of qubits that you repetitively use. So for example, for the 9-qubit case, the suboptimal circuit had 20 two-controlled C0 gates, so control, control, not, whereas the optimal circuit with all 9 qubits has 1971 8-controlled NOT gates, which are huge and very difficult to break into 1 and 2 qubit gates, which you'll need to do to perform it on a quantum computer. So massive reduction in complexity. So how does it compare? We again turn to this noisy quantum computer emulator. This black line is the optimal cooling with 9 qubits, and you can see that very quickly at low levels of error, it immediately starts to, heat up your system. But here is our line for the suboptimal cooling, and you can see that it's unaffected by noise till much later, and even cools more than optimal cooling with 5 qubits. So it does quite well. You don't have to give up a lot of cooling power in order to get a huge gain in resistance to noise. So I think I'm running out of time, but just very quickly, we tried to perform this on the real quantum computer. We just did optimal dynamic cooling with 3 qubits, and I don't want to take too long to explain this, but we tried it on 12 different 3-qubit clusters. It didn't work in 11 of them, but it did work in 1 of them. And the one that it did work in was actually the cluster where the qubit was at the highest initial temperature. We think that qubits on these IBM quantum computers, other quantum computers, are all initialized at the same temperature, but there's actually some variation. And the qubit that was actually at the highest initial temperature, the cooling did work for. So we think that's because it's a little less affected by noise. So still a long way to go, but we have a path forward for this. And I'll conclude by acknowledging my funding and my collaborators, and happy to take any questions.
Thanks a lot. Do you have an intuitive explanation for how you swap the heat from qubit to qubit? You showed a circuit diagram right at the end. Mm-hmm. I'm not fast enough to understand it, but if you have a 1-minute way of explaining it, that would be great.
Yeah, so what is going on in the cooling is you have your whole state space for the n-qubit system, and all the qubits start at an initial temperature, so all those states have some probability that's set by this initial temperature. What you want to do is swap these probabilities. All you're doing is using swaps, and you're swapping higher probabilities to states where the target qubit is in the 0 state. So think about 3 qubits. You've got 0, 0, 0, 0, 1, 0, 0, 1, etc. Half of those states will have the target qubit in the 0 state, so you're basically swapping the highest probabilities into those states. So yes, that's what's going on.
Hi, thanks for the great talk. I have 2 questions that actually connect to what was asked. So the first one is your circuit, it's designed to work with initial thermal state, right? Everything is
yes, we assume initial thermal state.
Okay.
All at the same temperature.
Okay. It's because I was wondering, and when you mentioned that the circuit grows exponentially with n, I was wondering if in the end you're in a way doing an arbitrary quantum state preparation, but in reverse. You start with an unknown state and try to send it to ground state in a way, and that's why it blows up.
Yeah, that is one way to think about it. And although we're sending to a degenerate state, because all we want is our target qubit to be in the 0 state, we don't care about what's going on with the other qubits. So there's a family of target states, yeah.
Yeah, so it's you're preparing the state of a subset of your qubits.
Yep.
Nice, thanks.
Hi. So I think there's something I missed when you showed the plots of the heat you can extract and then of the work. Because essentially, so you start with qubits all at the same temperature, you apply some work protocol to extract the heat. I don't understand how you can extract more heat by putting less work. It seemed like the plots you were showing seemed to indicate that, but maybe it's a matter of scaling because you talked about the work per qubit, but for the heat, it's only the heat for one single qubit. Is it?
Is this the plot you're talking about?
Yes, and because on the slide before, you were saying that when you are at low temperatures, you can also cool more. So I don't see how you can cool more by putting less work.
Yes, so it is the work per qubit. So as you add more qubits, yes, the total amount of work will increase, but the work per qubit decreases as the initial temperature goes down.
So is this also how I can understand that this is more efficient when you have more qubits? Related also to what you had on the slide before with the system size, or?
This one is saying that this is basically summarizing how it scales as you add, how the amount of cooling scales as you add more qubits. And so yes, it'll scale as 1 over n.
Okay, thank you.
Thank you for the nice talk. I missed one point. You mentioned that there are 2 species of qubits in the NMR, and how did you overcome this now in the current computers?
Okay, so that was for heat bath algorithmic cooling, where we're doing open system cooling. We allow our system, part of our system, to interact with the environment. That got very popular because these NMR quantum computers are at a high initial temperature, and so dynamic cooling wasn't good enough. Now I'm saying we only have identical qubits, so we can't use HBAC. But luckily, we have lower initial temperatures, and so dynamic cooling is now looking good and much more effective. Yeah, so we don't need 2 species anymore. We're just doing closed system dynamic cooling.
Can you talk a little bit about ions? Because ions use 2 species right now, barium and ytterbium. They cool one with the other. So is it related to what you described or completely irrelevant?
Okay, maybe you need to repeat the question. So for trapped
ions, trapped ions,
Yeah.
typically with continuum, and I think others, they use one species only for cooling the other one. So is it related to what you described with the NMR story, or is it completely
I'm not sure.
different?
I have not used ion-trapped quantum computers or trapped ion quantum computers. I was under the impression that they were all identical, but perhaps...
No. Right now, you have at least half of the vendors that are using 2 species.
I didn't know that. Okay, I'll have to look into that. Thank you for bringing that to my attention. So yeah, maybe heat bath algorithmic cooling would again be useful there. That's something to look into.
We can have one last question while the next speaker is installing.
I wanted to understand your initial temperature for the other qubits should be the same for all of them?
The initial temperature for the qubits, you're talking, in the model, yes, we assume that all our n qubits are initialized at the same temperature.
But, I mean, if temperatures are different, what would be the problem? Couldn't you use the same swap procedure?
Yes, you could use the same procedure, but the theory on what the optimal amount you can cool by will probably be slightly off. Yeah, but yeah, you could still cool with that.
But then in this case, you could use it even in the case of non-equilibrium initial state, right?
Yeah, I think so.
So you just need to understand what's the basis in which you have to look at each qubit.
Yeah.
Okay,
what we can say from our theory depends on them all being initialized at the same temperature. But if there's some difference in this initial temperature, I suppose you could derive different limits for the cooling. Okay, thank you.
Again.